I'm here to talk about PayPal data science, and you know, I was going to give an overview, but I thought it might make better sense if I tell you a bit more of a story. So instead of giving you an overview of PayPal data science, I'm going to call this transactions versus search. So basically, I'll be comparing transactions, you know, as commerce happens when people buy things versus when people search for things. Now, if these two things actually duked it out, what do you guys think will win? Who says transactions? Okay, search? No hands? All right, well, I'm a little biased here, so I can look at it over here too, okay. So of course, as I said, this is all in the context of commerce. So in that context, I would like to say that transactional data is a lot more valuable than search. If the question was either or. So first of all, just wanted to say that, you know, commerce is a huge, huge market. And some folks from Forrester say that in 2007, about 4% of online commerce was done among the whole pie, basically, right? So the majority of it is still offline, even today. But it turns out that a lot of the things that you buy is really sort of searched on the web as well. So what typically happens is, you know, you go to some retail store, you scan it, do the price check, go back and buy it yourself online. I mean, that's typical sort of behavior that's happening today. Of course, in the sort of the bigger picture, in 2013 at least, it says it's a $10 trillion market. And really, there's going to be a blurring between online and offline. And so in this context, I just wanted to say that commerce is freaking huge. And just a little bit about, at least a bit more about where PayPal is going. It's all about, you know, sort of, or there's another new buzzword, right? It used to be multi-channel, now they're calling it omnichannel. And it's really about omnichannel. So really what we're trying to do is make sure that if you want to buy things online or offline, it just happens automatically, automagically, regardless of what channel it is, and it's a seamless experience. So I don't know if you guys heard of PayPal here. I'm not supposed to say this, but it's a triangle blue dongle. You guys heard of that? It's instead of square, it's triangle, but don't quote me, please. Then we got the mobile, and then of course the POS. So, and on top of that, there's online. So wherever you want to buy things, we want to be there for you. So again, going back to sort of the story I want to tell you, the takeaway. By the way, this is in the States we call it takeout, but you know, it's not a takeout, it's a takeaway of this talk here, is when the context of commerce, transactions are greater than search. And I just wanted to sort of hopefully convince you by the end of this talk that this is indeed true. And believe it or not, I guess, you know, that is at the end of the day, if I convince you or not, it's actually factual. So does anyone know who this guy is? It's sort of a side story before I go into the main story here. This guy named is Viktor Frankl, and he's one of the folks who was very, very inspiring. He survived the concentration camps in the Nazi era. And basically, during his hard times, he said, between stimulus and response, there's a space. And in between lies our growth and our freedom, really. So what he's taught me is that between two things that I thought there was no space in between, he's created that space. And it's so deep and impacted all my life actually as well. So as a technologist, I'm thinking, like, how is this going to impact my life? You know, how can I apply this? And I thought that if you can actually create a space between two things that you think there is no space, I think that's where innovation happens. So going back to our main story, it's so funny, sorry. I never thought I'd put Victor and Homer back to back. But really, it's about trying to, for us anyways, trying to reverse engineer the part of the brain where it's all about commerce. And that's what really data science is about, is like, what makes a shopper tick? And we're trying to figure out at what context, at what, subject matter is a person searching for something, has a person transacted with something. So I'll sort of refer to Viktor in a bit, but I'm going to give a sequence of things that happen, at least, sort of in a shopper's mind as we're trying to create that Homer's brain, that small part of the brain. The reason why I use Homer is really because we're trying to reproduce a small part of the brain. I'm not saying there's general AI or anything like that. I don't think that's possible. But typically, when we think about a shopping behavior of a person, there's a certain sequence to it. So there's the want, discover, shop, buy, pay, and own. And as I talked about Viktor, some of the things in this sequence, I think there could be a lot of innovation that can happen when you can create spaces in between some of these sort of states. So for example, between buy and pay. It's like, what is the difference, and is there a space in between? And yes, there is, actually. So when you're buying something, you put it in the cart and you made up your mind. And then paying is actually, you don't really care. I mean, you take your wallet out and look at your share wallet and take something out and pay. So there's a space in between where it could be, for example, price elasticity, right? So when a person's made up the mind and between paying, is there a space in between where we can say, what's the best price for this person? Or can we apply some coupons? So there's lots of things like that that can happen in between. So think about like what's in between want and discover, in between shopping and buying. There are lots of things that can happen in commerce. Now, so let's take a look at this sort of sequence in terms of search. So typically, a lot of people start with search, right? I think a lot of, at least, me, like, I know what I want and just go search it, buy it, and I'm done. But typically, there's want. And then when you search for it, there's the discovery stage as well. When you search for a pink iPod, lots of pink different types of music players come up. And you go, wow, this is pretty cool. So you start shopping around and figuring out what's the best price, what's features. And then you try to buy, you try to make a decision out of that. But as from search, sort of the signals get weaker and weaker as we go towards own. So then you pay. And of course, at that point, there's search information itself does not necessarily point to predicting what you might want to buy. And then at the end of the day, you own. The way we look at things is we go the other way, actually. So we know what you own. There's over a decade worth of transactional data that we have. And then when you pay, it's all real time. When you pay, we know where you bought what. Then, of course, as we go towards upstream, the signals get weaker for transactional data. So at the end of the day, of course, we want to leverage everything you can and try to combine both search as well as transactional data. So in that context, let me give you some examples of the power of transactional data. And I'm just going to try to sort of limit that to that data source and try to tell you some stories about what we do. So we can't say big science without big data. So I'll talk a little bit about our data sources first, and transactional data, to be more exact. Well, there's 190 markets, so we're a global country, a global company, sorry. There's 25 different currencies, 113 million active users, 80,000 plus tables, got to be nerdy. And there's over 2 million attributes that describe our customers. I mean, that's a lot of description about our customers. And can you imagine, like, I can't imagine 2 million things that describe about me, but that's what it is. 70 hertz, does anyone know what that might be? That's the number of transactions we did in Q1 per second. And it equates to about $4,300 in TPV. So by the time I finish this sentence, we've transacted about $30,000. So this is what I call a transactional dance. And it's from one customer. I don't know if you can see that correctly here. One merchant in the US market. And it's, they do electronics, basically. And so the spikes are the number of transactions and volume that's happening, and it's all around the globe, right? And I just wanted to show you this part. Wait for it. Almost there. There. That was Black Friday. Of course, about the sort of, was it 25 different currencies. So this visualization, it's about transactions happening in one day around the globe. And the size of the balls equate to the volume of money. And the colors represent different currencies. And you know, it's an interactive glove. It's a fun thing. We have an iPad app for that, and people can swirl around and stuff. But it's really, really fun to watch just how much transaction happens cross-border. It's, you know, when I get bored, I just kind of turn that on and look at the transactions happening. Like, wow, that's really cool. So lots of really, I mean, it's kind of social, you know? I mean, it's between buyer and seller. This is what it means. One other quick story here. So sort of quick visualization before and after the Japan earthquake. This is before and right after the earthquake happened. You can see immediate 30% increase. And PayPal is really used for a lot for sort of charitable giving as well. So it's really enabled a lot of people to immediately pay and give as well. So another visualization over here over world, and the same thing. And you can see from here to here, just sudden increase of sort of volumes. So that's sort of the transactional data. So I guess hopefully I convinced you that there's a lot of data that's happening. And the question is, what do you do with that? I want to talk a little bit more about external data as well, not just sort of transactional data, but like things like search. But there are lots of different other types of data. And of course, we're not going to limit ourselves to just like what's the power of transactional data. Let's just limit ourselves to that. Of course, we want to add, you know, petabytes and petabytes and tons of data on top of that, so we can hopefully sort of reverse engineer the shopping part of the brain. Okay, so in the whole ecosystem, at least the way I see it, there's data, and there's data, and there's data. And this is sort of just sort of the brain fart, if I may, of some of the companies of external data, the sources that we have. But really, we start with the core of transactional data. And then if you think about eBay Inc., there are lots of different assets and properties there. Magento, eBay, there's, you know, Red Laser. Red Laser, for example, gets about up to 1 million scans per day. Like 1 million people using their mobile devices, going around you know, scanning things. And that's a signal for commerce as well, because it's typically what they do is they're price comparing. You know, should I get this or that, right? And they want to find out, make sure that they can go online and find out what the best prices are. Milo, we can get offline inventory, where we can get offline places database. So there's lots of different types of databases. On top of that, in the world, there's lots of social data as well as online data, and there are companies that are actually marrying both online and offline behavioral data together. So there's lots of signals here that sort of can really help us reverse engineer the brain. So that was big data. There are lots and lots of data. And of course, there are lots of people in this business as well. And I can't say big data without big science. And this is when we try to really sort of, from the data sources, how do we go about creating that part of the shopping part of the brain? So I'm going to do a little math. I didn't have, I'm in a different time zone right now. Sorry if I'm a little sleepy still. But I'm going to start with a simple math here. So there's a function f. I think we all know that. And you give it some input and gives you some output, a set of output, basically. So I'm going to talk about just a small piece of a technology that allows you to create similars. So given some input, it's going to create a set of similar things that almost look like that. Of course, some call it lookalikes. And try to give you a specific example first. So meet Carol. And this, of course, is a made-up name, but it's actually a real person. She's a working mother, and she's looking for toys, more specifically, Lego Star Wars. So for folks like, I don't know, Toys R Us, I mean, she would be an awesome, awesome customer. So what can we do here? Well, we have the function f that looks for similars, and we're going to plug in Carol to that and look for a bunch of similar Carols. And so what happens here is that, of course, we're going to be geo-locating these customers as well. And as they're transacting, we can find out what they're buying as well as who are similars to Carol all over the United States, basically. Second example, meet Bill. So he's a frustrated architect. He goes to Home Depot a lot. He loves Subway, and he's always looking for offers. So what are we going to do this time is that in the similarity function f, we're not going to put in Bill, but we're going to put in the Home Depot. So the question is, what are similar places to Home Depot? And you know, the reason why this makes sense is the question is, if Bill isn't the Home Depot, what are other places that he might want to go to? That's what this sort of a similar function looks for. So similar to Home Depot, you can see the Home Depot is in the middle, and the sort of places that are nearby as well as most likely for Bill to go to are in the sort of the next level of connectivity over there. And the reason why I can tell you that this data is correct, because if you look at right here, there's Victoria's Secret. So people who go to Home Depot also go to Victoria's Secret. I think that's kind of true, especially for men. And of course, there's Subway on the side. And we know that Bill loves Subway. And what can we do then? We can give an offer, 10% off his next sandwich, $2 off his next thing. So we'll sort of incentivize Bill to walk into that store as well, offline. Story number 1.5. It's somewhat related. But what we do here to really sort of think about how we score people also is we use a thing called RFM++ for predicting. So excuse all these numbers, doesn't matter really. What this means is that just by looking at transactional data that we have and some fairly basic model, we can predict where you're going to go and how you're going to spend your money next, up to about 70% accuracy. So what that means is that looking at historical data, and the question is, when are you going to spend money at Subways? And we can answer that with almost 70% accuracy. We've refined that a lot and add a bunch of other variables to it, and it comes up to like 93% accuracy. What that means is that I can predict with 93% accuracy if you're going to shop in the fashion category or not. I mean, that's really, really strong signal here. I mean, seriously, like if you go to Vegas and if you had 51% chance, like I'd be playing that game all day, and it's 93, so it's like, wow, it's phenomenal. So it's strong signals, and this is just from transactional data. So let me explain a little bit more about sort of how we compute the Bills and the Carols and sort of leverage some of the other transactional data as well. Another sort of cool example here is what we call a customer genome. So for every consumer, we try to map out their buying behaviors, and just from the transactional data as well. So it's a simplified version here, but on the rows, you'll see users and consumers. So there are 113 million rows, at least. And in this case, in the columns, you see the, the merchant category. So we sort of simplify that. So the users and the user RFM scores, and we have the sort of the industry categories. And basically, if it's in the light color, it means the person didn't really shop too much in that category. If it's darker orange, that means the person transacted a lot in that category. So it's somewhat all over the map at this point, but what we can do is, let's say we pick a lookalike, Carol. Then immediately, in real time, the system will put Carol on top and rank everyone according to the scores of their lookalikes. And the point of this visualization is that if you look at the genome sequence now, they're fairly aligned. That means whoever that first person, let's say that's Carol, we can figure out and rank all 100 million plus consumers according to how lookalike they are. This is a really, really powerful signal. So we leverage this to start, recommending things, targeting things, advertising, personalization, etc. Okay. So again, just sort of to show you some of the numbers that we have a bit deeper, we can sort of score everyone according to the lookalikes. And there's Hillary right there, and she shops at a fashion boutique store called Anthropology. And we're saying, okay, let's look for people that look like her. And the first one that came out was Trevor. And it's like, okay, so either Trevor's a cross-dresser or something else, because I was like, or we're wrong. But it turns out we weren't wrong. He's a fashion photographer. So we searched him, looked him up, and found that he's actually a fashion photographer. So he has a high likelihood to meet a merchant called Anthropology. So that means, can we offer him a coupon for that, or can we do something, or can we flash an advertising for Anthropology? So lots of use cases for him. Lauren's a 78% match because she does play a lot online, at least in a lot of games, but she does do a lot of fashion shopping. And Valentina, all she does is look for electronics and motorcycles. So she's only a 10% match. Ultimately, what we want to do is not just have transactional data, but of course have redemption information and data as well. So there are typically 3 R's that we look for: is reach, relevance, and redemption. And in order to get the redemption piece, we really need to start getting to a hot start state. What I'm trying to say is that in this part right here, when we use the transactional data to sort of take a first stab at the guess of where you might want to buy, it's still called a cold start. And yet, it's very, very strong in terms of what kind, in terms of where you're going to buy next. On top of that, if we can add some of the contextual stuff, as well as a bunch of other information, just demographics and things like that, and a bunch of other third-party information, I think this will create a strong signal in terms of creating that shopping part of your brain again. Okay, so I'm going to hurry through some of the slides here. Again, basically what it's saying is just looking at transactional data, we can also tell when a customer is going to churn. And with that, just adding more sort of third-party and other tables on top of that will start to increase its accuracy. And the beautiful thing about data science is that, regardless of how much data or how many rows or how many columns or how many, I guess, bits and bytes you got, it really doesn't matter. We just throw it in there, stir the soup, and the computer creates its predictions for us. It's really an oracle here. Okay, so now we're from transactional data. I'm going to try to give you some examples of how we add to that some of the other things. And of course, here everyone's probably thinking about social media. That's the next best thing. But what the F do you do with that, right? So at least in PayPal data science, I'm growing a team called sort of unstructured data analysis team. And a lot of them are background from natural language processing, NLP. So it's a structured way. It tries to understand unstructured data so that computers can sort of parse them better. And kids these days, like on Twitter, they say all these weird things that I just don't understand. So the language is evolving, and these things will continue to learn new vocabulary and new things, and new sort of structure of language as well. So what can we do with that? There are a bunch of things we can do, for example. So meet Pete. He tweets a lot about sports, music, as well as a bunch of other things, right? So what people tweet about, it really says a lot about what they're interested in, right? So what we do basically is we can cluster them, and we can also target them as well. So you see that Pete, and clustering is all about sort of understanding the natural language of things that they talk about. You cluster them, and it turns out that that cluster actually talks things about entertainment. So what can we do? We'll say, hey, with StubHub, if you pay with PayPal, you get 10% off your next sort of event that you want to go to, and target those guys. So basically what that means is that with transactional data, because we know what Pete's interested in, not just what he tweets, but we marry that with the things that he bought, then we cluster out there and figure out who are the lookalikes out there where there's a billion people out there shopping. What can we do them? What can we do with that kind of data? So then we look for and I think you guys get it, right? All right, so one other thing is that influencers. It's an important piece. And what I'm going to do is just sort of go to this piece right here and tell you why this is important here. So with natural language processing, you can do a bunch of things. You can extract people's sentiment. So is it positive or negative? What they're interested in, interest graph or topics or aspects, and influence. And those are the three things that are at least very important to think about. This one I'm thinking about just an example in sentiment here. So we've sort of went back in time and got all the Twitter feed and said, okay, people who talk about PayPal, what are some of the negative sentiments and where are the spikes? You see right here, there's a big spike. And we went back in time and said, okay, what happened then? And there was a regretsy incident where we took out a button for donations at a donation site. And basically that was for orphans during holiday season. Like, bad mistake. So there was a bad sentiment over there. Another one, we broke a violin. I don't know if you guys heard about that. Another bad sentiment over there. And then Elon Musk, one of the founders of PayPal, saying, PayPal is not in a good state. Another bad sentiment over there. So out of all these things, we can understand where people go, and then the point of that is that we need to marry that with the transactional data as well. And going back to the influencer, regretsy, it turns out that whoever had that website, she was a very, very influential person on the web. So if we knew that before, maybe we would have done something differently from a customer service perspective. Okay, so transactions versus search, of course, I think you guys understand it should be and. But in commerce, once you start with transactions, it's strong, strong signals in terms of predicting where people are going to spend next. Final words, nothing's impossible if you can imagine it. That's what being a scientist is all about. And this is guy, Professor Farnsworth from Futurama. Thank you. Thank you.
Absolutely. Yeah. So that concludes our morning. We're going to break for lunch now. Yes? I'm sorry? Oh. Wow. I can't even read. I am so sorry. So we're going to have Martin Wilcox, Director of Product and Solutions Marketing from Teradata Corporation, to finish our morning with one more vendor presentation on their view on big data. So Martin, thank you.
Thank you. Thank you, I think.
Absolutely.
Is this working? Good stuff. Just give me 1 second while I attach this here. So I am the guy keeping you from lunch. So please accept my apologies in advance. Good morning, everyone. It's a pleasure to be here. My name is Martin Wilcox. I'm with the Teradata Corporation. I'm Teradata's European Director for Platform and Solutions Marketing, I think they call me. But don't panic. I used to have a proper job. I used to be the data warehouse manager at a major UK retailer, and I've also been a solution and an enterprise architect. So they haven't sucked all the value out of me yet. So we're going to talk this morning about big data. And I want to go back and revisit some of the core assumptions that we're making about big data and review some of the core terminology that's used about big data. Because I think we're at some risk of getting ourselves into a little bit of a tailspin. And I think we really we've got to a point where big data has become so overhyped and presented as the next big silver bullet. And there's a long line of silver bullets in the technology industry, right? Cloud computing, client server, 3-tier technologies, thin client technologies. All of these technologies have ultimately added a great deal of value to information technology. But all of these technologies, at one point or another, have been posited as the solution to all of our problems. And I think we're all sophisticated enough to know that that isn't actually the case. I think it's time to revisit some of the core assumptions about big data and ask ourselves what it is, what it isn't, and how it can help our businesses. I want to start with a very brief introduction to Teradata. I promise you this isn't a sales pitch, but I want you to understand our perspective, the journey we've been on over the last 30 years, and the perspective that it's given us on information management in general and analytics in particular, and how that viewpoint colors our view of the future of analytics and information management. So 1970, I call this modern information management year zero. In 1970, Ted Codd wrote an absolutely seminal academic paper. Important to remember that in the technology industry of the 60s and 70s, data was a second-class citizen. Data was relegated to proprietary, application-specific file structures. There was no real meaningful concept of a schema. Data typically wasn't reused. It was up to individual application programmers to make sure that when they modified or read a file, they did so in a way that was consistent with the other application processes. We had multiple stovepipes of information across organizations. It was impossible to do cross-functional analysis. Customers very often had very, very many customer records, for example, with huge data quality and data consistency issues. And into this mess stepped Ted Codd with this paper, arguably one of the most influential papers and ideas, in fact, in information technology of the last 50 years. Fast forward 9 years, and 4 guys quit their day jobs, maxed out their credit cards, and built the world's first analytic database appliance in a garage in California. And the reason that this is significant is because in the intervening 9 years, most of the major implementations of the relational model, most of the database management systems designed to implement the relational model had been concerned with transaction processing, with building database management systems to support, for example, airline reservation systems. And transaction processing is a very interesting use case, but it's characterized by very many concurrent transactions, very localized access to data, where read and write workloads are fairly equally balanced. And analytics is a completely different use case. Analytics is global rather than local. We typically want to compare very many variables with one another. We typically want to integrate multiple subject areas together. So it's a global workload, not a local workload. And the guys at Teradata were really the first people to set out to build a system optimized for analytics on very, very large data sets. They made 2 key decisions when they built that analytic database computer in that garage in California. The first was that they would optimize the hardware and the software to work together with one another, and that they would pre-package that solution as what today we would call an appliance, what in 1979 they called a database computer. The second bet they made was on so-called scale-out architectures. So this was the first commercial implementation of the massively parallel processing model, where instead of scaling up, making more and more powerful processors, or having more processors connected to the same shared storage and same memory, this was a scale-out, a massively parallel processing architecture. And it's easy to forget now that during the 80s and the 90s, this industry was convulsed with debates about what was the right architecture for large-scale analytics. We had a group of vendors championing symmetric multiprocessor architectures and non-uniform memory access architectures, and another group of vendors led by Teradata championing the scale-out architecture. Well, today that debate is finished. Pretty much all of the major vendors now go to market with something that is recognizably a variant of the scale-out massively parallel processing architecture, and pretty much all of the vendors today go to market with something that's pre-packaged as an appliance. Because we started with analytics in mind, though, we architected the software in Teradata completely differently from the competition. The competition, by and large, has taken database management systems that were designed and optimized for online transaction processing and converted them to be parallel or semi-parallel in nature. We started the other way around. We built a database for parallel operation, for large-scale processing of data, for large-scale analytics from the ground up, and that's the reason that we continue to lead the industry. So that's really a little bit of background, and it shapes our perspective. We've been doing big data now for 30 years, and hopefully that means we've got something valuable to say about the future of big data. So let's talk about big data and where we are today. Teradata built its first petabyte scale database in the mid-90s. Today, we have more than 25 customers with more than 1 petabyte of data under management, and the largest production Teradata database in the world is currently at 40 petabytes and growing. So I think we have to ask ourselves, is this big data phenomenon that we've been talking about for the last 2 or 3 years, is it actually real? Because clearly the tools, the technologies, the management approaches and processes that enable us to build very, very large databases have existed for some time. So is this a real phenomenon, or is this vendor hype designed to ship more hardware and more software? Well, I think it's a little bit of both. But I think to understand what's real and what's hype, we need to revisit some of the foundational definitions. Any presentation about big data must include an obligatory exploding data volumes chart. So here is my obligatory exploding data volumes chart. You can see we're living through an era of exponential growth in data volumes. Now, we have to be a little bit careful with charts like these. Remember, the thing about exponential growth is it implies a doubling every so often, a doubling every roughly 2 to 3 years at the moment. But of course, we've been living through a period of exponential growth in data volumes for a very long time already, actually. And we've largely managed. Those of you that have made smart architectural choices, smart technological choices, have been able to build very large databases already. So I'm not sure that size by itself should be something that ultimately concerns us too much. The other thing I think it's really interesting to look at, this is the IDC research. I could have used, there are a number of different research studies which all produce sort of similar charts. The reason I've used the IDC research here is because IDC make an attempt to differentiate between what they call business transaction data and what they call web application data. And you can see that at the moment, the principal growth in data volumes is from what IDC call web application data. Now, I actually think it's a slight oversimplification to characterize all of this data as web application data, but nevertheless, this distinction is very interesting. Structured business transaction data volumes continue to increase. And from an analytics perspective, they continue to increase faster than this blue line would suggest. We see growths in data warehouse volumes in the Teradata customer base of roughly 40% per annum. So a database that's 10 terabytes in size today is 20 terabytes in size 2 years from now. But the real driver in volume is this web application data. So what is this web application data becomes a very interesting question. I said before that I think in this industry we tend to suffer from a lack of good definitions, and very often that is encouraged by vendor marketing departments who have a vested interest in there being some ambiguity about the definitions, so all sorts of products can be branded as all sorts of things. So let's go to the source of all knowledge on the internet. Let's go to Wikipedia and look at the Wikipedia definition of big data. Definition. Big data is a term applied to data sets whose size is beyond the ability of commonly used software tools to capture, manage, and process within a tolerable elapsed time. Big data sizes are a constantly moving target, currently ranging from a few dozen terabytes to several petabytes of data in a single data set. Now, I don't mean to sound critical of people that give up their spare time to advance the sum of human knowledge, because there may be some of you in this room, and you're much, much better people than I am. I'm far too selfish to give up my time for free, and I don't have so much to contribute either. But this is a terrible definition. I mean, this is hopeless. What is a tolerable elapsed time? In the US now, in some states, they're polling vehicle sensor data in near real time to establish when there's been an accident so they can prioritize the response of the emergency services. If you're the dispatch controller and you have 4 paramedic crews and reports of 5 accidents, tolerable elapsed time is measured in seconds or milliseconds. You have a very short period of time to make a life or death, a literally life or death decision. If I'm the marketing director at a big retailer doing a complex behavioral segmentation of my 40 million customers, a tolerable elapsed time is the time between me pressing enter, walking across the road to Starbucks, and coming back with a cappuccino. So a tolerable elapsed time tells me nothing that's useful about this problem space. And then let's look at this range. A constantly moving target ranging from a few dozen terabytes to several petabytes of data in a single data set. Well, I'm a physicist by training, not an engineer. I'm happy if I can calculate something to the nearest power of 10, 1 order of magnitude. But that's a 3 order of magnitude range there. So that doesn't tell me anything that's very useful either, I don't think. This list of examples, however, this list of examples is much, much more interesting to me. Examples include weblogs, RFIDs, sensor networks, social networks, internet text and documents, etc., etc. You can read so I won't go through the list. But with one exception, with which I also take exception, call detail records, all those data have one thing in common. Anybody tell me what it is? All too busy waiting for me to finish so you can go to lunch. All those data sources are non-relational. This is what's interesting about big data. Size really doesn't matter. It's the nature of the data. This is what's interesting about big data. And this is really the key takeaway that I'd like you to take from this presentation. Big data are typically non-relational or multi-structured. Text, with all the natural language, natural variation and ambiguity in language that the previous speaker was talking about. Voice recordings, social network data, machine log data and scientific data, for example, seismic data. These are what's really characteristic of big data, not statements like ranging from a few terabytes to several petabytes. Typically, most of us capture and exploit these data in our enterprise data warehouses in our analytics solutions today. And so it's interesting to ask ourselves, is this a trend that we as enterprise computing professionals need to worry about? Is this significant? Where is the value for my organization? Well, at Teradata, we think the value to your organizations is this. Typically, what we capture in analytic databases like enterprise data warehouses today is transaction and event data. If we're smart, we integrate transaction and event data across multiple subject areas, and we've used that data, that integrated information resource over the last 30 years to do incredible things, to optimize supply chains, for example, in ways that weren't imaginable 30 years ago. But we're principally still concerned with transaction and event data. And in very many cases, we have extremely limited insight in the interactions with customers, with suppliers, with partners that lead up to a decision to purchase, a decision to defect, a decision to churn. I'll give you a very simple example. My bank, every time I call them up, there's a nice recorded message that says, this call is being recorded for quality and training purposes. Now, we're all sophisticated adults, right? We know it's not being recorded for quality and training purposes. We know it's being recorded for the purposes of dispute resolution. If I have a fallout with my bank, and there's a debate about who said what to whom and when, it's very important that there's a record that can be recovered so we can establish exactly who said what to whom and when. And I'm fine with that. But in my bank, I know this for a fact because they're a Teradata customer, in my bank, that call isn't leveraged for any kind of analytics today. What a waste. I mean, think about it, really. With appropriate digital signal processing technology, you can understand whether that call was placed from a quiet or a noisy location, which could tell you something about how you design your IVR systems. More interestingly, with appropriate digital signal processing technology, I can tell about your state of mind from that call. I can tell if you're relaxed or if you're stressed. I can tell if you end the call abruptly. Now, when I call the bank, you see it's very often from a noisy location, and I am very often stressed. And that's because I'm doing the banking on a Saturday morning whilst trying to babysit the kids. And in my house, at least, that's an extremely stressful endeavor. But say I call the bank, and I'm stressed, and I'm calling to make an insurance claim, and I recently increased the value of my insurance premium, and this is the third, shall we say, dubious insurance claim I've made in the last 2 years. You should probably send a loss assessor to see me before you pay out on my claim. This is the kind of insight we can potentially extract from these multi-structured data, and the kind of knowledge we can then have if we integrate that insight with the structured data that we're already capturing in our data warehouses. So let's look at some big data. Let's look at some multi-structured data. This is an extract from a weblog. I'm not going to pretend it's representative of all big data, but it is multi-structured data. It is machine log data, so I think it's worth looking at this data. I'm no weblog expert, but with a very quick visual examination of this data, I can see that it's potentially incredibly interesting. I can see that the user didn't come directly to our website. They were referred from Google, and I can see the search term that was used to refer them. I can also see that they're not using Internet Explorer or Safari if they're a Mac user. They've gone to the trouble of downloading Firefox, which tells me something about the kind of person that's visiting the website. So potentially incredibly valuable information about the consumer that's visiting the website. So hands up, how many of you are capturing weblogs or machine logs in the database types that the major vendors have added to their products over the last 10 years? Binary large objects, character large objects, user-defined types. One hand, two hands. Two hands in a room of 100, 150 people. Right, that's not great return on investment from the vendor perspective, right? We went to a lot of trouble to introduce those data types into the products. It's relatively easy to capture multi-structured data in the data warehouse. The reason that most of you aren't doing so is because it's the devil's job to exploit that data when you've got it there. You have to write user-defined functions. You have to write them over and over. It's very difficult to parameterize them, to do multi-column comparisons. So it's not that there isn't value in this data, and it's not that we can't capture it in today's database technology. The challenge is exploiting useful information from those data. This is a quote from the Economist Special Report on Big Data that I think is really quite profound. We are used to the idea of deploying new technology to improve productivity and efficiency, but data are no longer merely the byproduct of process improvement. They are becoming the raw material of business. This is very interesting to me because I've seen this journey at first hand with structured transaction data. I started my career a little less than 2 decades ago at Asda in the UK. At that time, Asda in the UK did not collect electronic point-of-sale data from the stores. It was literally waste, a byproduct that was left on the floor of the stores. Those EPOS systems had been installed to improve cashier productivity, because improved cashier productivity means shorter lines at the tills and better customer service, and to reduce fraud. Fast forward only 2 decades, and there isn't a serious retailer anywhere on the planet that doesn't capture and integrate that data in a data warehouse, use it to drive all facets of the retail operation. And in fact, we now see this going even further. We increasingly see the journey from business intelligence to consumer intelligence, where leading organizations like Asda are opening up their data warehouses to end consumers. Asda in the UK now, if you shop at Asda, you can take the receipt home, enter some key data from the receipt. There's an online query to the enterprise data warehouse that tells you how much you paid at Asda and how much you would have paid at their leading competitors in nearby locations. So we see this journey all the time of data initially being the result of process improvement, of automation, and subsequently being collected for analysis. And we're starting to see this being played out with the new data sources as well, with the multi-structured data. This is data from a Teradata customer. It's a vehicle manufacturer. The average family car today contains 60 to 70 microprocessors and sensors, and they were not placed on the car to capture data for analysis. They're the systems that control the engine management systems, the automatic braking systems, the airbags. But these systems create data which is incredibly valuable for analysis. This particular manufacturer has an automatic intervention system in the car that will apply the brakes under certain circumstances. You can see here the speed at which that intervention system is typically being deployed, the target angle of the object that the car is trying to avoid. All of these data have incredible value for analytics. They can tell us about whether there are blind spots in the car that we need to address in the next version of the car. They can tell us about whether the braking systems are indeed effective enough. We can use them to develop new driver aids because somewhat counterintuitively it turns out that the majority of interventions are at low speed rather than high speed. Systems that were not deployed to produce data for analytics, and that data is already being repurposed for analytics. Took 20 years or more in the case of data like EPOS, the structured transaction and event data. It's happening much, much more quickly where the multi-structured data sources are concerned. There's something else I think about big data that's very important and very profound, and that is that some of the new technologies are enabling us to do new types of analytics on existing structured data. This is vehicle warranty claim data. This is a temporal correlation, a path analysis. You can see there's a very high positive correlation between faults in the infotainment system and faults in the seat system. Probably what that's telling us is the actual fault is in the electrical subsystem. It's being manifested initially either as a problem with the electric seats or as a problem with the infotainment system. But when we know about this correlation, we can plan vehicle servicing completely differently. If somebody comes in with a problem with the seat, we know we need to go and look at the wiring system. We can use it to do root cause analysis. So some of the new technologies also have application on the data that we've traditionally been collecting for the last 2 and 3 decades. We can now see and analyze that data in new ways, ways that weren't previously possible. I think one of the other interesting side effects of some of the big data technology is it enables us to invert the traditional business intelligence model. I've used a kind of mining analogy here because we often talk about data mining. It's expensive business mining. I went on holiday in the southwest recently. The southwest of England is covered with disused tin mines. It's a very, very expensive business mining, right? You have to sink mine shafts, you have to organise proper ventilation, pumping systems to do the drainage, you have to get the mine product to the surface, you have to deal with the waste. Huge capital investment required before we extract any value from the ground. And so we want to be confident that there is actually something worth extracting before we begin, which is why typically we do some kind of prospecting. In the Wild West, in the Yukon Valley, a bearded guy with a pan, and today with sort of modern seismic techniques. I think there's a clear analogy between mining in that sense, in the traditional sense, and some of the advanced analytics we can now apply. You know, the traditional role of business and IT is somewhat being subverted by some big data technologies and some big data approaches. Traditionally, it's been the business's job to define the questions of interest to the enterprise. It's been IT's job to go and source the data that can answer those questions, structure it appropriately, devise, extract, transformation, load processing that can populate the target data model and build applications that allow the users to ask those questions. But some of these new multi-structured data sources, precisely because they're so novel, we are not yet sure which parts of the data are valuable and which are not to our particular business, and exactly what types of analytics we need to perform in order to extract that value. So increasingly, we see a lot of organizations very interested in collecting large volumes of data that may be of value at some point in the future. Now, if you're collecting large volumes of data because they might one day be valuable, you have a very different focus on cost than you do if you're up here in this kind of traditional BI model. And we'll come back to that in just a moment. So these new programming models and these new technologies, I mentioned before that they're enabling new analytics, in some cases on new sources of data, the multi-structured data, and in some cases on existing sources of data. Everyone's talking about MapReduce at the moment. MapReduce is becoming another one of these silver bullets, these holy grails. Important to understand that MapReduce is just a parallel programming model. It's a parallel programming model like the other parallel programming models that are instantiated in products like IBM DataStage and, of course, the Teradata database management system. The interesting thing about MapReduce is it's the first generalized and open parallel programming model. And what that means is the complex procedural logic that we need, for example, to do digital signal processing on voice recordings, we can now write these algorithms as MapReduce algorithms and potentially run them in parallel across a wide range of computing systems. In parallel means we can process lots of data and/or we can process that data very quickly. And of course, across a wide range of computing systems is very interesting from an enterprise architecture perspective. Important to understand, though, that big data is not equal to MapReduce, and MapReduce is not equal to Hadoop. Hadoop is just one implementation of the MapReduce programming model. This is data that's reproduced by permission with eBay. eBay has two very large Teradata systems. They're the bar on the left and the right here. This is a traditional enterprise data warehouse, if you will. This is a key value store based on Teradata Extreme Data Appliance. It also has a Hadoop cluster. And eBay wanted to measure and understand the relative performance of its Teradata systems compared with its Hadoop systems. This first measure is system unit cost normalized. And you can see Teradata's not coming out of this comparison too well. If we look at some other metrics, though, computing units consumed to do a particular piece of work, this particular test query, then Teradata comes out much better than Hadoop. If we look at the normalized job query cost, again, Teradata much cheaper than Hadoop. If we look at latency, the performance, the response time of the database management system, the SQL-based system, is much better than the Hadoop system, and that turns out to be a function of parallel efficiency. So really important to understand with all of the new big data technologies that are emerging in the marketplace, they all have different strengths and weaknesses and different sweet spots. And the idea that there is one big data technology to rule them all is, I think, completely wrong and something we need to be very careful about. The other point to make is this was an extremely simple query in the end, a basic table scan and summation, and you would expect some of these variations to be even more extreme for a more complex query. The other thing about MapReduce and its various implementations in Hadoop that it's key to remember is it's just a parallel processing framework and a programming model. It's not a database management system. And this is a joke that Mark Madsen originally came up with. He's a very influential guy. If you don't follow him on Twitter, you really should. We've got an IT guy and we've got a business guy. And the business guy says, so how do I query the database? And the technology guy says, well, it's not a database, it's a key value store. Business guy says, well, I don't care. How do I query the key value thing? The IT guy says, you write a distributed MapReduce function in Erlang. Did you just tell me to go to hell? I believe I did. Now, it's a funny joke. But while it's like this, we are never going to realize the potential of these data sources and these technologies. According to some of the more excited commentaries, and for the record I agree with them, some of this technology has a transformational potential for business akin to the development of the telegraph, the development of the railway, etc., etc. Well, if we seriously expect big data to to have the same kind of impact on our businesses as the development of the railway, then it needs to become much, much easier to use. I think it's interesting to ask ourselves, how do we industrialize regular, traditional business intelligence over the last 30 years? And for me, a big part of the answer is SQL. SQL, for all of its limitations and for all of the frustrations about the fact that every vendor has their own dialect, it is a standard. And the existence of that standard has enabled the industry to develop lots of tools, lots of applications, which enable us to access data, which enable ordinary analysts and end users to access the data. If this was the secret to industrializing traditional business intelligence, then I would argue that we need similar standards if we're going to industrialize big data analytics as well. And this was the motivation for Teradata's acquisition of a company called Astrodata last year. Astrodata is an MPP database management system like Teradata. It has a number of analytic engines, an SQL engine, also a MapReduce engine. Remember, Hadoop is just one implementation of MapReduce. And critically, it speaks SQL. So ordinary end users can invoke MapReduce functions using this SQL MapReduce interface. It's like calling a table operator, if you will. Here's an example of this in practice. This is data from a retail finance company in the US. And these, I apologize, I know it's an eye test. These are events across different channels. And what we're doing here is we're doing path analysis. We're looking for a characteristic path that leads up to the defection of customers. This is extremely difficult to do with SQL. It's extremely difficult to express with SQL. This type of analysis in SQL requires us to write multiple self-joins of the big transaction and event tables to one another. That's relatively computationally inefficient, and it also assumes that we know the degree of the relationship that's interesting. If we know that we're interested in 3 degrees of the relationship, we write a 3-way self-join. But what if the question is, how many degrees of the relationship are relevant to this use case? That's a very, very difficult thing to do in SQL. It's trivial with MapReduce, and it's trivial with the Asta product, which includes a MapReduce function which you can call from SQL. It turns out in this particular analysis that fee reversal events are extremely significant. If a customer calls up and says they want a fee reversal and you don't give it to them, you better be prepared for them to leave. Very quickly, let me discuss some architectural considerations. Second key takeaway from this presentation, it is not one big data market, not by any stretch of the imagination. If we think about traditional set-based analytics, if we think about non-traditional analytics, time series, path analysis, graph analysis, if we think about structured data on one hand and multi-structured data on the other hand, there are a number of different segments. There's this requirement to capture, store, and refine large volumes of multi-structured data and extract relational metadata from it. There's a requirement to integrate all the relational metadata in enterprise data warehouses, and there's a requirement to do these non-traditional analytics on the data. At least 4 different segments. And remember what I said before, the different technologies have very different strengths and weaknesses, very different sweet spots. Let's quickly skip through some of this material in the interest of time. Final thoughts on all of this from me. We're living in the era of data superabundance. The corollary of Moore's law is that simple computing devices are now incredibly inexpensive. That's why there's 70 microprocessors on your car, all generating data, all of which potentially have value for analytics. Think network data in telecommunications, 10 times more detailed than the traditional CDR data that we've all been capturing. But not all organizations are equally well placed to extract value from this data. I love this quote from Hal Varian, Google's chief economist. If we're serious about industrializing big data BI, we can't be asking end users to write distributed Erlang functions. We need better tools, we need better standards. Size matters much less than structure. If we were doing it all again, we really shouldn't have called it big data. We should probably have called it big analytics. It's the multi-structured data, the multi-structured nature of the new data sources which is interesting. It's the iterative types of analytics which are difficult in SQL which are interesting. And lastly, do please remember, the only reason for pursuing one of these initiatives is to deliver business value to your organization. As a vendor, we see a lot of organizations tire kicking at the moment and wanting to start a big data project, any big data project, to keep up with their peers. That's a recipe, in our view, for wasted investment. We now have 2 technology offers, an integrated active data warehousing platform. Remember, integrating data is still critical, and a MapReduce-enabled platform to enable you to process that multi-structured data and to do that non-traditional analytics. It's been a pleasure to be with you this morning. I hope you find the rest of the conference useful, and now I think you finally get to go to lunch.
Thank you very much. Thank you very much. Okay, so we're going to rewind, and I'm going to give you the little 5 minutes that I had before I forgot, so I apologize. Thank you. This is the end of the morning session. We'll be breaking for an hour for lunch. We'll be coming back at 1 o'clock. We'll be splitting the session here into 3 pieces, so please pick the session that you want to come to, and you'll be enjoying that. I'm going to leave you with a thought, though, before you walk out the back door, to kind of put this whole big data thing perhaps in a little bit bigger context. And it's something we've been talking about at Forrester for a while, and that is the fact that what we're seeing over and over is businesses realize that they're moving out of what we call the analog age into the digital age. And what that really means is if you take a look at all the processes and the things that you do as a business, and a lot of those things that you do are based on scarcity of information because all your processes were analog, right? Well, if you think of the fact that information is really digital first now, that all this information is available, all this digital data is available, and if you're relying on that digital information to really guide your business, you can begin to shed all these analog inefficiencies and move really fully into the digital age. And the key to dealing with all that digital information is this thing we're talking about, big data. So that's the opportunity that we have. So thank you for attending this morning. We look forward to this afternoon. Please join us for networking lunch. Thank you.